And without further ado, our next speaker is Sandeep, which is going to tell us about Numpy in Graphland. A round of applause for Sandeep.
Thank you. All right, hey. Okay, so this talk is about something I've been playing around with on my spare time. So some of my work involves using graphs, and while I was graphing along, I had this idea, what if I could turn this graph into a matrix and do things with NumPy, which is not a novel idea at all. It's like a very standard representation of a graph. So, I deserve no credit for any of this. Anyhow, before I dive in, I'm going to be going pretty fast. So if we are not all starting on the same page, I have to apologize. All right, so let's get into graphs. So graphs represent connections between entities, right? So that's a graph. The bubbles are entities. The lines between them are connections. More formally, the bubbles are known as nodes. The lines between them are called edges. So that's a graph. Okay, so networkx, I don't know if you've, it's a pretty popular Python package. Typically, probably the first thing you would reach for if you're working with graphs. I mean, unless you're working with really big graphs, in which case you'd go for like PySpark for graphics or whatever. But yes, networkx, it's really good. It's really cool, super full featured. One of my favorite packages. So the way networkx represents graphs is as a collection of dictionaries. Right? There's a little more going on, in there, but this is the gist of it, right? It's a collection of dictionaries. So why I mention this is because this representation also drives the kind of algorithms that networkx comes packaged with, right? Okay, so alternative representation for graphs is as matrices. So every graph G, including this one here, has an adjacency matrix corresponding to it. So this one has 8 graphs. That's an 8 by 8 adjacency matrix. So you can flip back and forth. So for every pair of nodes that have an edge between them, there's a 1 in the graph, right? And if a pair of nodes doesn't have an edge, there's a 0. So that's the adjacency matrix representation. So this is pretty much exactly the same information as in this picture, right? So completely one-to-one so far. And yeah, so now that we have a matrix representation, I'm going to use NumPy to manipulate matrices and see if I can turn graph algorithms which are typically not written in matrix fashion into sort of matrix language. Right. So, but why would I want to do this in the first place? Right. Apart from just curiosity. So because of a couple of good things that NumPy offers. So NumPy gives me access to C code, which is presumably faster than the pure Python that networkx offers you, right? And NumPy also gives you vectorization. So if you haven't heard of vectorization, if you're doing operations on big vectors, instead of going over the vector one by one, the CPU will essentially handle them in mini batches. So you'll get a speed up there. So for those 2 reasons, I was hoping to see a speed up in the algorithms as compared to the more traditional like graph iterative based approach. And sort of in the longer term, I mean, this is not something I've tackled just yet, but machine learning is a thing. So because of all the activity around machine learning, the infrastructure for what I call big matrix or big linear algebra is rapidly maturing. So I'm in the long term, I'm interested in where that can take graph analytics as well. So yeah, so this is kind of why I did this. Okay, let's dive into some graph algorithms. First up is breadth first traversal, also known as breadth first search. I just refer to it as BFS. What BFS does is essentially builds up a succession of layers, right? So you start at a node, you go to its neighbors, that's your first layer. Neighbors of neighbors, second layer, neighbors of neighbors of neighbors, and so on, right? So start at node 0. You go to its neighbors, 1, 2, 5, 4, and 5. So these are the ones that are directly connected by edges. And next step in the iteration, you go to their neighbors, right? So you have, what do you have there? Well, the other nodes. You have the other nodes. Okay, so essentially, in the language of matrices, it's a matrix vector multiplication. So how can we see this, right? So let's go back to the very first step of the BFS here, right? So I've shaded the source of the search, the zeroth node in blue, right? Yes, 5. Okay. So corresponding to that that shading, we have this vector here, right? So I've colored, I mean not colored, only the zeroth element is 1, the rest are all 0, right? Now, what happens when we multiply this by the adjacency matrix A? We get another vector, which it turns out represents the neighbors of the zeroth node, right? So essentially, you can think of the adjacency matrix as as representing something that will propagate things through the graph along the edges, right? So in this case, you started a node and propagate to its immediate neighbors. So you can essentially repeat that multiplication and go to the next layer of the BFS. It's not quite as simple as that because you also have to deal with the case where like you don't want to go back to nodes that you have seen before, so you kind of have to handle it a little bit differently. But yeah, essentially it is a matrix vector multiplication.
Wait, that was just the first column, right? I mean, the multiplication you did, because it was just a 1. Just a 1 in the first position and zeros everywhere else, right? So you're just getting the first column. I mean,
you were not getting the, oh yeah, you are essentially getting the first column, yes.
Yeah.
Yeah.
So why not just take the first column?
Sure.
I mean, like,
yeah, you could take the first column,
okay,
yes. Yeah, because, I mean, so in general, you're repeating this multiplication multiple times, right? So the next time you do this, you'll be multiplying by this vector, not the first column. First column is because the first column contains the neighbors of the first node, yes. Good call out there. Okay, so next algorithm, triangle count. So, oh boy, okay, that's a triangle. 3 nodes, all sharing an edge. And the reason you would want to count triangles in a graph is because it's a good measure of the density or the connectedness of the graph, right? So if you're doing social network analysis, for example, and you're wondering how connected your graph is, this is a good metric to keep in mind, right? And in matrix land, this is a matrix multiplication. Specifically, you're multiplying the adjacency matrix with itself. And the code for it is literally a one-liner. It's basically magic, right? So you multiply the adjacency matrix with itself 3 times, and you get the number of triangles. And the reason for this, I mean, so the mechanism is very similar to what we saw in BFS, right? So it's a propagating thing. So multiply the adjacency matrix by itself, and you're essentially doing a 2 times propagation. So you have a instead of connecting to your immediate neighbors, you're connecting to your neighbor once removed, as it were, right? So that's what happens when you square the matrix. So you cube it, and you get a bunch of triangles. So yeah, it's a really cool algorithm, and very succinct. Third algorithm, all pairs shortest paths. The problem here is finding the shortest path between any 2 pair of any 2 nodes in the graph. So that's the shortest path between node 3 and 5. So length 3, there's no other shorter path. And if you want to do this for all pairs, you end up with the APSP problem, right? This is kind of weird. In matrix land, this isn't your normal linear algebra. It is a min plus matrix multiplication. If you want to get all mathy, it's a semi ring on the tropical numbers. I don't know what the tropical numbers are, but I believe they're real. So just trust me. There's an algebra where this is a sensible multiplication. And that's what the multiplication looks like. I mean, if you want to look at the code, but yeah, so that at least that's what squaring the matrix looks like. You're multiplying the matrix with itself. Now, if you do this n times, where n is the number of nodes in the graph, you end up with the distance matrix, which right away solves the APSP problem for you. The distance matrix is every element represents the distance between the corresponding 2 nodes. Okay, so performance, right? So this is the reason I started out on this path. So happily, it does better than the usual networkx algorithms. I haven't really tested them on super large matrices or super large graphs, but also I haven't made a whole lot of effort into like optimizing this, right? Anyway, so here you see the comparison. The x-axis is logarithmic, the y-axis is running time in seconds. So smaller is better. And the bright orange is the NumPy or matrix version. The pale blue is the networkx version. So we see similar speedups for triangle count and all pair shortest path, right? So nothing super interesting to see here. Kind of what I expected. So that's great. But yeah, I mean this is not something I've really pushed to its limits yet. So like the matrices that I've played with simultaneously kind of small and also kind of big because there are thousands of nodes, but also the way I generated them, we have at least millions of edges, so they're reasonably sized. Okay, so what do we learn from here? We have faster code. The code is also super succinct. I mean, we had a literal one-liner for the triangle count. The memory usage is kind of up in the air. This is not something I've measured. I'm expecting it to be bad because my very naive implementation did not use sparse matrices, which you typically want to do with graphs because most of your adjacency matrix is going to be zeros, right? So that is work for the future. Sort of the flip side of the succinctness is that the code is obfuscated. Like you can't really tell what's going on there. I mean, the pseudocode looks just like the Python code I showed you. So it's just a bunch of matrix operations. So kind of have to spend some time figuring out what's going on in there. Another downside is some of the information is lost. I mean, this could possibly be improved with slightly more, craft around the algorithms. But for instance, if you did the usual iterative triangle count, you would end up with a list of the actual triangles, which in this case it doesn't quite give you. Right? You get the number of triangles, but you don't get the actual triangles. So similarly, similar issue with the paths. You don't get the shortest paths; you just get the distance between them. Okay, so cool way to think about graphs and graph operations in terms of matrices. If you want to play around with this, turns out there are already some implementations, so you don't have to build your own. Specifically, SciPy has a compressed sparse graph routines module, which I discovered really late. Turns out there are also some NumPy-based routines in networkx itself. So yeah, had fun playing around with this. That's all I got.
All right, so while our last speaker of today sets up, which is Al, are there any questions? All right, well, I'll start from here and I'll work my way back.
At the holiday party before last, Richard Heidegger discussed how in the heap algorithm, he could save a lot of cache hits by the organization of the operations. In your matrix operations, wouldn't it be possible to try to renumber your graphs so that it is the width from the diagonal is shorter and that you could then have fewer cache misses?
I don't quite see how that would work. I mean, these would all be square matrices. You could renumber your graph, but I don't know if that's necessarily going to make your matrices smaller. I mean, you could try making your matrices sparse matrix, like you could represent it as sparse, which would take up a lot less memory. But yeah, I don't know if renumbering would actually. Well, okay. I mean, this is not something I know. So yeah, no comment.
Hello.
Yes.
I was wondering if you had explored at all how any of this would translate to directed graphs.
Okay, good question. No, I have not. So, I mean, yes. So, some of it should transfer. I mean, so, it's still linear algebra. Only thing is the matrices are not going to be symmetric. So, I don't see why it shouldn't work. But yeah, it's not something I've tried out yet.
Over here.
So in physics, something you try to do is split things out into eigenvectors, basically orthogonal matrices. If you do that in this context, what does it tell you about the graph?
Interesting comment. I have no idea. I mean, so I know that graph eigenvectors are kind of a thing. I don't know what they mean, so I don't really have an answer for you. Yeah, but yeah, thanks for sparking that thought. I'll probably play around with that.
Sandeep, we have a question here.
I was wondering, did the dot product have any kind of meaningful interpretation? And did you look at maybe, because this is like a 2D graph, kind of like on a plane, but then you could imagine like in chemistry, like a molecule, like a 3D thing, if you explored that, or if there was any kind of like mention about those kinds of stuff.
Okay, I'm not really sure where to look. Okay, let me answer your second question first. So this isn't necessarily a 2D graph in that it has a 2D embedding. Like this could be, this could be a graph that doesn't have a 2D embedding. So there's nothing fundamentally two-dimensional about it, right? So you could imagine graphs with multiple kinds of edges, which you can't represent just using a 2D matrix, which would take you into tensor land. So you'd have like a multi-dimensional matrix, as it were, one dimension for each type of edge. Yes. The dot product, I don't know. I mean, depends on what you mean by the dot product. Like in NumPy, np dot is basically just matrix multiplication, which we kind of saw what it means. But if you're talking about the dot product between two vectors, like yeah, I don't know. I don't know what that vector would be in Graphland.
It's the inner product of Traversal and scalar.
Right. Yes, but I don't know what it would represent.
What are the vectors anyway? What are the vectors anyway?
Yeah, I don't know what the vectors are. Yeah.
Yeah, we have time.
Okay.
So quick comment, there actually is, contact matrices are used in molecular structures. Turns out if you want to ask questions of the form, if I have two atoms within some cutoff distance from each other, and you assemble a matrix of those, that becomes your adjacency matrix. And then you want to say, I now know that A and B are within that cutoff distance, and B and C are within that cutoff distance. An effect in A, in principle, has a transitive effect on C through that distance. So that's actually been used for decades as a way to assess the impact of change on a distant part of a molecule.
Anyone else? All right. Thank you, Sandeep.